In this video we will talk about the limit of a function. Okay. Now if you remember, in a previous video we looked at the definition of a tangent to the graph of a function. So what we did in there, we said we started off with a point on the graph of the function. So let's call this y equals f of x. Okay, and we looked at, we fixed this point and we took another point on this graph of the function and we looked at the line connecting these 2 points. And so this line was a secant. And then we moved this second point a little bit closer to the first point and we got another secant to the graph. And we kept doing so. Okay, so what we did is we tried to approach on the x-axis our point A, maybe from both sides, okay, with this family of secants. And we said that if we figure out that this family of secants actually approaches a given line, that given line was going to be called the tangent to this graph. Okay. Now, let's move away a little bit from this idea of secants and tangents, but still stay with the idea of us approaching a certain point and not necessarily touching the point, just approaching it. Okay, so let's say, okay, we've got the point A on here and we got the point L on the y-axis. So these 2 points determine a point here of coordinates A and L. Okay. Now I'm going to draw a graph of a function, and then as I will draw it, I'm going to point your attention towards what happens on the y-axis, because on the x-axis actually nothing magic happens as long as we are allowed to get close to our point A. And what does it mean for us to be allowed? As long as the function is actually defined closer and closer to the point A, this discussion makes sense on the x-axis. And the actual behavior, interesting behavior, is on the y-axis. Okay, so let's say maybe this function starts off by increasing towards L. Okay, now it even touches the point L on the y-axis, and maybe it keeps going up. All right, and then maybe decides to turn back down. Okay, again we crossed through the line y equals L, so we went underneath it, and then maybe we go above it again, and then we go underneath it, and so on and so forth. All right, now remember that this discussion is about the graph of a function sort of trying to approach this point. Now when I look at this graph here, I see that, well, okay, we try to approach this horizontal line, so our function eventually gets to be equal to L again and again and again. So that's okay, that's encouraging actually. But at the same time, what I see happen is that my function still goes away a lot from this horizontal line here. As you can see, let's call this extreme points, it's away a lot, and it doesn't seem to be willing to get closer to this point here. All right, so that's actually discouraging. At least at the intuitive level, it doesn't look to me like this red curve here tries to approach our point. Now I'm going to draw in blue another graph, okay? And let's sort of analyze what happens to this next graph. So let's say maybe this graph still goes up, okay, it approaches this horizontal line, okay, it goes up above it, it goes down, okay, maybe it goes up again and down again. All right, so basically now I see, still see this oscillating behavior, but that's okay. Not all functions are as simple as a linear function or as a quadratic function. So we can see these oscillations, all right? But what I see different from the red graph is that even these extreme points, okay, even they, as we approach A on the x-axis, even they approach our point L. okay, on the y-axis. So that's a huge difference between the red graph and the blue graph, okay? So that's what happens at the intuitive level. So and this idea of us approaching this point here, L, would be that if we draw a band around our point L, a horizontal band like so, no matter how narrow we pick it, I see that this blue graph eventually makes it into the band. The blue graph is in the band, but the red graph, it still goes up away from this band. That's not the behavior you want to see if you want to sort of see the graph of this function approach the point L on here. Okay, now let's move on to this system of coordinates here, because this one is a little bit crowded now. So what we are going to do, again, let's take another point A on here. All right, and let's take a point L on the y-axis. So what we said during this discussion here, we said that what we want is that no matter how narrow we pick a band around L, okay, so no matter how narrow this band is, we want to be able to find a band around A, okay, so that as soon as we are into this band around A with our point X, our function will stay in this horizontal band, okay, so that's the idea. We want to be into this box, all right, so now what I'm going to do is I'm going to pretty much repeat what I just said, but I'm actually going to write math for it. Okay, so what we said is that no matter how narrow this horizontal band is around L, okay, how do we write this into math? It means that if I pick here some epsilon, a positive epsilon, okay, and I'm going to pick sort of a horizontal band symmetric with respect to this line, y equals L. So which means that for any epsilon greater than 0, right? So no matter how narrow this band is, turns into math as to us asking that no matter what epsilon is greater than 0 that we choose, okay, as soon as we are into this band, okay, so what does that mean? It means that we can actually find this band here, this vertical band. So there must exist a certain delta, okay. Let's say this band, I want it symmetric around the point A. So there is a delta greater than 0, okay, such that, okay, whenever I'm into this band, what does it mean? It means that whenever I have an x here on the x-axis, so that is close to A, meaning that the absolute value of x minus A is less than the half of the width of this band, which is delta. Okay, so whenever my x is close enough to the point A, meaning that is at most of distance delta from A, but not necessarily A. I don't care about the point A itself. All right, so if you remember this discussion we had on this graph, we took points closer and closer. So I don't really care what happens if x is equal to A. Okay, so whenever we pick an x with these properties, then I'm stabilized in this box here, meaning that I'm at most epsilon away from L. Okay, which means that f of x minus L is less than epsilon. All right, so this is the epsilon delta definition. All right, so this is just a definition. All we need to do is make sure we understand it at the intuitive level, and at the math level.